We will try today to finish with some more example on the progress in membrane reactors. And we have been discussing reactors at a high temperature, with basically in gas phase as hydrogen production or water gas shift or steam reforming and similars. We have been discussing about also membrane bioreactors, which are the one more interesting at the moment. In both cases, remember, it's nothing more than just combining molecular separation with one membrane operation. At the moment, normally are when you are making this integration is ultrafiltration with a traditional bioreaction, but much more is coming. And I give you one example now of a case in which system reaction, traditional one, oxidation, normally reaction of oxidation, can be redesigned based on catalytic membranes and realizing a catalytic membrane reactors. This is interesting because this can be just a way to redesign a catalyst. An area of interest today is for making progress in catalysis, is how to use the catalyst. Often you have very interesting catalyst that you study in the lab and you make your experiments, they show an interesting activity, etc. But when you move to real application, there are a lot of troubles. Trouble can be related to problem of poisoning, interaction with some of the reactants, instability, problem with temperature, increasing temperature, you have coke formation, and the lifetime of your catalyst is becoming very short, so not interesting for industrial application, or eventually, when you go in scaling up, etc., in a real system, the specificity of your catalyst is not the one expected that you have when you work in a clean atmosphere or in a clean bath, etc. So that's an interesting case because by what is called here heterogenization, that means nothing more than immobilization of your catalyst in a polymeric membrane, room temperature, so we don't have any problem of high temperature, nothing strange. We can have some interesting progress for the family, for one family of catalysts, which are the polyoxometallate. These are interesting catalysts, well tested, a lot of publication in the literature, etc. But when you go to real application, there are problems related to how to recovery, about the cost, about the stability, etc., etc. The possibility to realize a system, as we already discussed with enzyme, for example, in which the performance of your catalyst, when combined, when designed not as a pellets, not as a fluidized beds, powder, or column, etc., but compartmentalized or immobilized in a membrane is quite interesting. That's why it's a case that we like to discuss, and we will see that polyoxymetallate are quite important family of catalyst. They are this anionic cluster of early transition metals, as MO, W, vanadium, etc., and oxygen. Complicate structure, as you can see here, and there are a lot of these catalysts under study, under investigation. People expert in this area, organic chemistry, etc., they just synthesize more and more, and they try to study the catalytic activity, particularly in oxidation. Oxidation is one of the most complicated reaction systems to keep control, because you can have a lot of changing in temperature very often, and there is oxygen around. That means it's one of the problems that can be becoming dangerous. So there is a lot of this study in progress, and in photochemical reaction, you can have some, you need some increasing of the temperature sometimes to activate your reactant, but they can be used as green oxidants, and they are stable with respect to thermal and oxidative degradation. And that what is interesting, when they are in an acid form, as acid, they have superacid properties. Superacids are important for different reasons. For example, you are using superacids in a fuel cell. Superacid means that is high percent of protons can be around, and protons are the one that you are using in a fuel cell to transfer produce electricity. We will discuss also this. So that is one of the area of particularly of interest. Anyway, in general, is one field where people are analyzing carefully this. And the area in which this kind of reaction are important, as you can see here, are significant. All the hydrocarbon transformation, that means all the petrochemical industry can be involved in this. Sometimes just in fine chemistry, that means specific, very selective oxidation of some organic substrate. In wastewater, the area in which, for example, we have been working is in the problem to try to remove phenol, which is complicated chemicals that is create a lot of pollution, not easy to have its degradation, and that is one of the areas in which we have been working. And that's why this system has been under investigated. Remember that basically we discussed last time, if possible, we are trying to use non-covalent supports. That means there are different ways to immobilize your catalyst. And this way can be just by formation of film, deposition on a surface, adsorption, or covalent binding, or non-covalent binding. Non-covalent is the best way of trying to do it, because there is less problem in changing the specificity of your catalyst. When you have chemical links involved in the mobilization, the probability that there are some modification in the catalyst behavior exists, so we are trying to avoid as much as possible. This is a typical example of immobilization of one of these compounds, a decatungstate, in polymeric membranes as an efficient heterogeneous photocatalytic system. That is, there are regions in which basically what is important that the specific activity of the catalyst overlaps the area in which there is the solar emission. That means you can use you don't need to use any lamp, etc. You can use the solar emission for activate your catalyst. And this is one of the area in which this biocatalyst can be quite interesting. This is one of the cases in which we have been working more, this W10O32, complicated structure normally, and which is quite interesting for some aspects, but there are different drawbacks, some negative aspects. For example, the low quantum health, the relatively poor selectivity, and also limited stability for pH different than above 0.5, basically. What is possible to do with membranes in principle is just what we have been discussing already. We can reuse and reuse this catalyst, because when immobilized, you can just clean or separate from the reaction volume, so that you can increase the total turnover number by recycling in a certain number of runs. This can be quite significant number. We can model, we can tunnel, change a little bit the selectivity as a function of the substrate affinity. As I was mentioning, when you immobilize your catalyst in a certain environment, the function of the polymeric phase, hydrophilic, hydrophobic, supplying electrons or accepting electrons, can significantly change the overall behavior of your catalyst. So that can be done here. You can changing the affinity of the catalyst to the substrate, the polymer you are using. That means changing the kind of polymer. This system can significantly change, and the effect of the polymeric microenvironment on the catalytic stability and activity is another area of interest. That is in principle the kind of system we are discussing. In this case, just as I was mentioning before, the possibility to use just the solar energy is quite attractive. The membrane material, the first thing when you are doing this kind of work, you have to check the condition that you have to respect for being sure that the catalyst can operate. In some case, when you mobilize your catalyst, or you can completely destroy the possibility, for example, that the system is stable. So you have to check the stability under the irradiation condition to see if the catalyst will work. Eventually, which kind of properties are necessary in terms of hydrophobic or hydrophilic for the kind of reaction. In this case, it was a reaction of organic substrates in water, so the hydrophobic properties is one of the aspects that you have to check. And that the material that you are just utilizing, you also have to be sure that there is no specific competition in terms of absorption or just as eventually catalytic effect. Sometimes the polymers, some kind of polymer have a specific catalytic effect that can have an influence and competition with the one you are adding. So you have to decide basically which kind of polymers you want to use. So you cannot just decide because it's nice to make a membrane with PVDF. You have to be sure that this polymers is appropriate in terms of hydrophobic or hydrophilic, depending the reaction, is stable under the irradiation, there is no competition in the absorption with the catalyst itself, etc. So this is a preliminary study to be done, not easy. And when we made it, for example, we made mistakes. We had no idea about, and we have been using PVDF and PMDS and PDMS, and you will see that not all these polymers are appropriate. At the end, after making this study, you will realize that the system in some situation is working, some other one is not working. And that's what you have to expect. For example, in this case, you have the catalyst dispersed in DCM solution of PDMS for this kind of a polymer. At the end, has some performance very different from the one that is dispersed in PVDF. The TBA W10 is much better dispersed in PVDF than in PDMS. This dispersion is important to control the reaction, to avoid the clustering of the catalyst in the polymers, to have homogeneous distribution as much as possible in the system is very important. In these two cases, you see in one case it was working, in the other one it was not working. The dispersion was much worse in one of the polymers, then that is a very traditional polymer that everybody is using, is a rubbery polymer for making membranes, for gas separation, etc. So this one, forget. Very good membranes, but not appropriate for making, for immobilizing this kind of catalyst for sure. After making the membranes, you have to check what I was mentioning before, and to be sure that your catalyst is still acting as a catalyst that you were aware before. And so you have to check these, the different level of absorption in the region of the interest, in the frequency for your radiation. And you can see here that by the infrared, etc., the catalyst structure is well preserved in this PVDF membrane that we have been testing in this case. So that is one of the things that has to be done. And now when you have been doing the membranes, charged with a certain level of catalyst, I don't see here there are data. Oh yeah, there are some data up here. You have to be sure, by the way, the amount of catalyst you can immobilize, which is directly related to the behavior as a catalytic system. More catalyst, more efficiency, and this behavior, however, you cannot increase. If you will do the study the system, you will see that when you're increasing more than 20, 25%, 30%, you can start to expect two problems. One can be leakage. That means during the operation, when you put the system in operation, slowly you can lose some of the catalyst in the solution. And you don't want to do this because we want to recovery and to reuse as much as possible. So you have to optimize in terms of the percent of the catalyst that you are adding to your to the polymeric system. And you are also changing, by the way, the mechanical properties that can be in some cases in positive, some cases in negative. You can have an effect that you are producing a kind of composite material, and depending from the size of your particles, from the kind of system you have at the end, you can have a better improvement, some in elongation and tensile strength. Some other case you are inducing some weakness in the mechanical properties, some fragility, and you break the system. So this is one of the areas that you have to analyze carefully, and you see here that you have to check at 25%, at 33%, eventually with the same level of thickness in such a way that you know which the parameter that really is affecting the final problem. And that the amount of catalyst obviously that you are putting, for example, that was a reaction that I was mentioned before, quite important. There's a lot of pollution related to the phenol in the water. Phenol is produced in big industrial production, in, I don't know, stainless steel production or in some other similar industrial sector. You can have this kind of a product that you'd have to discharge in the wastewater. So if you can make a degradation, and that is something that is interesting. We found a certain percent, about 25% of the catalyst in the system is the one giving the better performance. You can have here, as we discussed last time, a diffusion control or a kinetic control system. And the diffusion control, it means that if you charge too much and you can, part of the catalyst is there but does not work. The probability that your reactants just arrive on the catalytic sites, for having a catalytic reaction, you need a physical contact between the substrate, the reactants, and the catalyst. And if you just have a too dense system or a block system with no easy permeation, etc., you're just having trouble. So there is trouble in leakage, trouble in mass resistance, to the, not easy to arrive to the catalyst, etc., etc. All these things mean that you have to work in a different condition, check the situation. And here are data that are showing the effect of the transmembrane pressure on the degradation. That means the contact time that you can see here, and increasing the transmembrane pressure. When you are increasing transmembrane pressure, basically what you are doing, if the system works, you are decreasing the contact time. The penetrance is moving faster, and you can see here that we have a certain transmembrane pressure from 0.5 to 1.5 bar, 38 is becoming 15, and if you just now analyze it, this is consistent with the experimental result that you obtain here. With this, the system just work as, and also here you have to try to optimize. You don't know, it's not easy to anticipate the results. So the only way is doing a lot of experiments and trying to optimize which is the most interesting transmembrane pressure for the specific reaction, for the specific catalyst that you are studying. And again, now at this point, we know which kind of loading is interesting, 25%. We know roughly which is the transmembrane pressure we have to apply to have a contact time appropriate for making good, having a significant conversion. And now you can try to study this phenol degradation and basically the phenol mineralization, that means the disappearing of the phenol in the system, and the result can be quite interesting. That is the case in which we have been using this kind of, this polymer, this kind of catalyst. Now, if you want to change it, to improve the system and doing something better, the situation is much more, again, more complicated than expected. By the way, this is a comparison between the homogeneous and heterogeneous degradation. And you can see here that the heterogeneous degradation is giving some more interesting result than the data that we can have in a homogeneous system normally. And the efficiency, particularly in terms of lifetime, the polymeric environment is very well, it can be considered a system to protect the properties of the catalyst that you are using, but much better than just having the system free in your homogeneous system. You can also have different way of doing. This is just by using phase inversion, basically. You can just make this kind of membranes by using the same properties that some of you are studying today. PVDF is the same polymer, and some of you is adding for increasing porosity, you are making some additive that are positive in porosity in pore formation. And you can use, instead of this substance, you can use a catalyst, but the methodology is the same. Basically, what you expect at the end, increasing the percent of the additive, can be a catalyst, can be a pore-forming materials, can be something different, the story is the same. And so you can have this kind of effect. Now that there is also a system you can try to make with plasma on functional IPVDF membranes. You can just have a grafting of nitrogen containing surface, and such a way that they can just have an interaction between the catalyst and the surface that you activate by a plasma system. So there is different way of doing, and eventually all this to trying to increase the stability in real operation, and these are systems that has to operate. It's quite interesting, one of the problems that sometimes you have, and in which you have to find solution. And I will show you one kind of solution that is in this case, but this can be generalized in many other cases. If you want to work with different kind of polymers, for example, here is this iflon. Iflon is a quite interesting polymer. You mentioned is an amorphous perfluoropolymers. As one problem, very expensive. There is not a big market for this because it's used in the space technology and similar. This is a polymer that today, if the production will stay at this level, costs you something as the intrinsic value eventually between $15, $18 per gram, not per kilo, per gram. In the market here in Korea, if you want to make some research with iflon, you must be very rich, because that will cost you, they sell you about $38, $40 per gram. So if you want to have 1 kilo to cast membrane, etc., you need a fortune. You need just 1 kilo of polymer is about $40,000. So you cannot play too much with these kind of things. If you are lucky and you have the polymer, you can try to do different things, including trying to immobilize a catalyst in the structure. Why this? This is a very strong resistant to all environmental oxidation and reduction. Is resistant to a lot of solvents. Is quite hydrophobic, and so you can utilize for making hydrophobic seals. So it's quite interesting one. And now, how to do? You can take your catalyst, the same W10 that we have been discussing before in one of its form, and try to disperse in here, and try to have an homogeneous distribution, the one that we are trying to have. Otherwise, the catalyst does not work in an appropriate way. If you do this, that's basically the results are not interesting at all. This is what the kind of structure you have at the end. There is basically no wettability between the catalyst, this W10, and the polymer that you want to utilize in this case. So no homogeneous dispersion as we obtained before and with other polymers, etc. On the other side, for some reason, sometimes you have to use something as iflon or similar, because the property of this scaffold, of this polymer, are quite important for some specific application. So you have to find a solution. These aggregates are very bad. We don't want to have this. And that means no interaction between the catalyst and trap and the polymer matrix. Poor dispersion of the catalyst, that means bad catalytic membrane. So what you have to do in this case, there are different ways of doing. The one we have been doing, we're lucky having some people expert in the fluorochemistry, and is this kind of solution. In some case, you can just try to functionalize your catalyst. Having this catalyst reacting with some appropriate substance, which just create a specific new system in which you predict, and then otherwise it's not easy to do, you have to know what can happen. You can predict that this kind of modification, this group that you are binding to the catalyst, don't change the catalytic properties, and these people must be expert in doing this, but in the meantime, these are all fluoro compounds, and that can help very much the wettability that we were not having before in the previous system. So that was done, and this is kind of recipe for trying to do in this kind of situation. And compared to the results before, as you can see here, the kind of how this system is relatively changing. That is the presence of these cationic fluorophilic groups on the decan-2 states allow a very good dispersion of the catalyst, much better than the one that we were observing before. So that is a kind of interesting result, but for doing this, you have to know a lot of good chemistry, because it's not obvious that this kind of, first of all, if we had to solve by ourselves, there was no idea what this kind of compound existed, what can be done without killing your catalyst. And when they were suggesting this kind of things, my first reaction was, this will be a different catalyst, because with all these complicated, but if you are an expert in this kind of system, in the kind of functional groups and in the kind of catalyst, you can tell no, the effect is not severe at all and can be done. Was done, and that is interesting results compared to the other one. Many other kind of reaction actually can be attempted, but that means that is a way to solve a situation in which in the literature people before were telling the system does not work. You cannot have this kind of distribution will kill your idea to make catalytic membranes. Not at all. With some good modification, at the end you have this kind of distribution, and the system works very nicely, and you have a good reaction. Keep in mind, another interesting way to solve a problem of this kind is also the one, this encapsulation, that you can have kind of a liposome. There is a lot of substance in nature in which they are able to create this cell. Well, that is the morphology that what is happening in the system we are using is something sometimes happen in nature, because this kind of substance just they try to protect the catalyst by forming this kind of a double lipid double layer that looks as a kind of biological membrane. But there are a lot of these kind of situation that good chemists can try to utilize. This cationic amphiphenyldesk group, this RFN+, induce the self-assembly of the surfactants encapsulated clusters, which during membrane formation give supramolecular assembly to the catalyst stabilized by the polymeric matrix. So all these nice droplets that you see here, they were nothing more than this kind of system. That means the system has been reorganized itself, forming this kind of droplets in which your catalyst is blocked inside, etc. So that's quite ideal. That is a very good reproduction of what nature is doing. And keep in mind, however, that after doing this, another problem exists very severe, that you say, okay, very nice, and you start to work on it. You can change significantly the performance of your catalyst, change the size of the droplets, which is in principle relatively obvious, because this possibility to the amount of catalyst you mobilize, the problem of mass transfer is also related to the size of the droplets, obviously. But that is an example in which this dimension of the cluster can be modulated, acting on the way to make membranes. And when you make your membranes in the lab for any other matrix mixed membranes, the same kind of effect are here. Not just changing the thickness, changing the amount of catalyst you put in, the temperature at which you make the phase inversion, and that is all parameters that can give a significant influence on the final performance. And that is at the end just working on this kind of system and this kind of reaction with this kind of catalyst. Here are quite interesting performance that you can obtain by the increased significance that you can see from this one to this last two, this kind of total conversion, this 500, 600 is becoming 3,447. So if you become expert and you know how to handle the system, you can have, starting from this, you can arrive down here. And that is just already accepted possibility from a scientific point of view, quite interesting in this case, but also in many other ones. just to show that if you go in literature today, in this area of catalytic membrane system, not the traditional water gas shift, steam reforming, that there is a lot of work but not too much realized. But you can find a lot of, much more just in today, also in the room temperature, in traditional reaction, as this phenol story, and that can help to solve a problem. So this is another area, not too much. No, 10 years ago there was nothing basically in this field, no membrane were utilized. Today more and more this is an area where you can, and it's huge, because you can do everything basically. Okay, so we had different examples of membrane reactors. First case, as we have been discussing, of a system in which we can try to have what we call a multifunctional reactors, where more functions are present, molecular separation and chemical reaction in ones, but there are many other possibilities still to be explored and quickly to be published for the people who are going to work in this field. With this we can stop here, and we will just eventually rediscuss in the next classes some other example of membrane reactors that today are under study. And we move to another topics that we are supposed to cover, which are the fuel cell. Is already here? Yeah. No, I think I found it. Yeah, here it is. In principle, this is totally different topics. Is not, because you will see, as we mentioned already, that fuel cell is a system very much related to the capability to produce membrane reactors. As we discussed already, when for most part of the fuel cells, as we will see, are related to hydrogen production. The one more utilized today are just hydrogen is the fuel we are using. And remember that we discussed this, because hydrogen does not exist in nature, free, so you have to produce hydrogen if you want to operate your fuel cell of any size, a small one, big one, etc. And for producing hydrogen, the way in which you want to produce, particularly if you're talking of relatively small size, that means for transportation, plane, train, your automobile, etc., you don't have a huge amount of space, you have to make everything small and very efficient. The way in which, if you go in literature and you on the web, you will find already some patents from big company, and there's Shell, BP already suggesting that you put all this system for producing your hydrogen in a suitcase that can stay on the back of your car or under your car, and they are a system where you receive your gas, and eventually you take gas just from the gas station, as today already can be done. But your gas is through a steam reforming, is producing hydrogen, and the steam reforming is a membrane reactor, the double tube that we discussed last time. And after the steam reforming, this cleaning part, you go in a water gas shift, and you learn why, because in water gas shift, all the CO, most part of the CO, you can transform in something not poisoning the catalyst at the end, which is this 10 ppm of CO is the maximum that can arrive on this the catalyst. And this was the water gas shift section, like very compact, small reactors. And after this, eventually you go through another final purification, palladium membranes, because they are 100% selective only to hydrogen. And finally, you arrive to the traditional cell. So that is the system that people are trying to consider today, the integrated fuel processor, where we have membranes everywhere. These membranes for the production of the hydrogen, are membranes for the decreasing of the poisoning, are membranes for the final cleaning of the hydrogen, and finally are the membranes, as we will see now, in the fuel cell. But these are not the only membrane that are necessary. Before the one in the fuel cell, you need a lot of other membranes before, otherwise the fuel cell will never work without all these other compartments, particularly in a small scale and so on. And this kind of system, this kind of, if you read this report I was mentioning in our introduction, for how the industry will be in the 2050, you will find that the prediction that we are doing and a lot of other people are doing, 2050 basically engine, combustion in typical engine system will not exist anymore. Everything will be electricity related to fuel cell. So there is a lot of motivation and interest to develop a fuel cell for a lot of application, from a big system for distributed power generation to stationary power generation, transportation, and all the different systems that we are normally utilizing, where electricity is the form of energy that we want to use. Electricity can be produced through the fuel cell, as is well known for you. The motivation are here. By the way, there are different kinds of fuel cell, and we will see some of them. But basically, the motivation for all the fuel cell that we can realize are that the very high efficiency compared to any other system in which you have a Carnot cycle in between. The efficiency that you can have in a fuel cell is approaching 70%. With the Carnot cycle, where you have, when you have heat to transform in mechanical kind of work, you have 20%, 30%. Here in this system, in principle, you can have about 70% efficiency, which is the highest percent of the conversion today possible. Maybe tomorrow people will do better, but today this one. As all the membrane system, they are very modular. You can have a small one, you can scale down, scale up, the same concept, the same chemistry, the same ideas can be very easily transformed. They are the efficiency as is related to this, as we discussed in all membrane operation, are not related to the size of the plant. You can have the same level of efficiency in a small or a big one, and in principle, low environmental impact. In principle, because this kind of system are extracting oxygen from the air, are supplying hydrogen on the other side, and the final byproduct is water. The reaction that we are considering is production of water, reacting hydrogen with oxygen. So just the opposite. Not only is not environmental impact, because water is not a problem, but is a way to produce water. When you have this, you go in this space and you have your people living there, water is not coming. But sometime now also they have this shuttle going up and down, taking also water, fresh water, good water. But the other water is the water that you are producing by yourself. And you, thanks to good membranes, you can recycle the most part of this water, or this produced by the fuel cell on board, producing electricity on one side, but producing water. Unfortunately, this is also the origin of accident, because the first, the case of big and the first Gemini that exploded, etc., was for some not good functionality, function of this system, in part related to membrane also problem. Because the membrane here we will see has the function to keep separate anodic reaction from cathodic reaction through a membrane selective only to hydrogen going through. If everything works, and the same is for eventually battery with lithium, no problem. But if something does not work, for any reason, can be a leakage, can be a hole, etc., you mix oxygen with hydrogen, etc., in a not appropriate way, or in presence of a cut of some temperature, etc., you have blowing up and everything exploded. And that was the origin of the first Gemini problem. Okay, so that is some of the benefits. What is the external configuration of a fuel cell is here. As you can see, what you have normally, you have on one side you supply your hydrogen coming from the system that we've been discussing before. On the other side, you supply your oxygen, and this, you have a problem of hydrogen oxidation on one cathode, you have on one electrode, you have a problem of oxygen reduction on the other one. They migrate through the membranes, which is selective only for hydrogen, proton, H+, and so you produce basically water as byproduct and electricity if the electron that you release during this oxidation reaction will be just circulated across the system, as we will see. That's interesting that if you do this kind of thing, remember that in terms of environmental impact, that's the best way to reduce this amount of CO2. CO2, as you just are reading every day, for the first time for them country as China decided to keep control of the CO2, they are starting to be also afraid of what is happening around the world. And the fuel cell, in principle, compared to coal, which is the one they are burning in a huge amount in China, this is the production of CO2 using burning coal, and this is the production of CO2 coming from a fuel cell system. So you can see here there is order of magnitude reduction. These are more than about 2-3 order of magnitude reduction in the production. So it makes a lot of sense trying to reduce as much as possible this and trying to produce at low cost and with high efficiency this kind of system. High efficiency means good electrodes where you make your oxidation reduction and good catalyst for doing this, but more than this, good membrane to making the operation. That's why membrane people are involved in this. So again, the system I was mentioning before, keep in mind that here, fuel cell is nothing more than the normal battery, all the equation that you have been studying, discussing lithium battery eventually, or the typical battery that you learn at school in the first class, the Nernst equation, and potential of oxidation, potential of reduction that are moving the electron, etc. All is the same. And you can produce on the basis of this kind of understanding a reaction between copper and cobalt, or copper and nickel, the one that would be oxidized, the other one reduced, releasing some electrons, and you make battery of type 1. And that means battery that during the reaction, the cathode and anode will be chemically converted, and when they are converted, you put in the garbage. They are just no more conversion is possible. There's another kind of system which the chemical reaction taking place at the electrodes can be reversible. So you have something that has been oxidized, something that has been reduced, but when this system is over, you change the polarity and just the reverse is taking place. So you start again with the same as the beginning, battery of second kind. And you have this what we call accumulator, the one you have in your car, this is the lead accumulators, or the new one that exists today, lithium is one of the cases that can also operate in this way. And there is a third kind of battery, this one. Where is the difference? What is the main difference? What is different in this kind of battery, this kind of cell, and the type number 1, type number 2? No difference in the basic concept. No difference in the equation controlling the phenomena and the electrons. Only one difference. The two previous ones I was mentioning are systems which you have to supply, to put something in the battery, and you make your package, and it's done and stay there. And eventually you can restore the properties, but it's always in a system very well closed system, basically. And the first kind is so close that when the reactions are over, you put in the garbage, in the appropriate garbage, by the way. Specific one, because there's a lot of catalysts and metal, etc., don't put in any kind of garbage. These ones are open system. So the only difference between traditional cell, number 1, number 2, is that in the normal cell, everything is closed and is there. In the system here, you can continuously supply the fuel and the oxidant to the system. And that means that you can have a plane flying in the sky or a train, etc., in which, when necessary, you just continuously resupply the system and they never stop if something does not break in the cell itself. So that is the situation in which you have a fuel and on which you have the oxidation, and it's going to the anode, and during the oxidation you release some electrons. These electrons will be moved outside, and they go on the other side where is the cathode, and where an oxidant will be reduced, and with using the electrons that are coming in, and you close this electrical circuit by a ionic connection, and the ionic connection can be just here. Instead of making electrolyte, that must be a ionic solution, some ions. Here is the connection is electron that are just making the connection. Here is ions making the connection. You can have a solution, water and sodium chloride. That will be the same job. However, that will be difficult to handle, a lot of space, etc. So instead of using a traditional electrolyte, you can use a solid electrolyte. Solid electrolyte is ion exchange membranes. That means a system in which ions can be transferred, as we not with you, as we mentioned in our previous class, when you make electrodialysis or this kind of things. And there is polyelectrolyte that can be positive charge, negative charge, and they can just operate. In this specific case, what we want to move from one compartment to the other is H+. So that will be a membrane specific with what we call a transport number equal 1 for H+. Has to be the highest possible, only H+ has to go through. If something different can go through, we can have a problem. We decrease the efficiency first of all, but you can have a problem that can kill the people. That means unlike the classical battery, we don't store the energy within the chemicals internally. There is no chemicals that you have to block here inside, and they will be converted with time. No, they use a continuous supply of fuel from an external storage tank. That can be the back on your car, that can be just methane. The methane will become hydrogen. The hydrogen is going to the one electrode, will be oxidized and will be reduced on the other side. The electrode within a battery reactor change exactly as in the system that we have been describing. Advantages, you can see here, basically, as I was mentioning, zero or near zero CO2 emission. Very, very low compared to coal and compared also to oil, etc., etc. And just to give you some number, you can produce, this number are changing every day, but anyway, less than 1 ounce of pollution for 1,000 kilowatt hours of electricity produced, compared to the 25 pounds of pollution or pollutants for traditional system. Very low noise eventually, reliability and simplicity, modularity and easy scale up and scale down, very high energy efficiency, and that is again something similar to what I was mentioning already before. It was also interesting in terms of energy efficiency I was mentioning before. If you plot here the energy efficiency as the power output per kilowatts, you can see that the fuel cell are up here, and all the other system, internal combustion, no competition. And gas turbine, simple cycle, combined cycle, etc. Basically, fuel cell, if well done and if well realized, are competing with order with efficiency. I was saying today is better than this because that's I know the data can be about 70%, not just 50, 60, but you can also arrive to 70%. And this again is if you make any comparison, you can see here is number. The heat engine combustion that you're normally using today, etc., the electrical power plant or transportation efficiency is about 20-35%, 30-37. Here is 70-80%, 40-50%. So no question, and that is today. Hopefully, if some of you will spend time doing good research, etc., these numbers are going to increase and not to decrease. How many fuel cells we have and how we can classify them. Here is a typical table where you can summarize the one existing, let's say yesterday, not today, because every day we have something new, but basically the one we will discuss a little bit more are these, the one where this contact between the cathodic and anodic compartment is done not through a ionic solution, but through a solid ion exchange membranes, basically. And that's what we call polymeric electrolyte fuel cell, basically. Polymer electrolyte membrane fuel cell. And that's the way to realize them. You can have also this alkali fuel cell. This country has some good know-how in this area, for example, and also this solid oxide fuel cell or phosphoric acid fuel cell, in which this a function of alkali, phosphoric acid, or molten carbonate is a way to produce. If you have a carbonate and you melt at high temperature, this is working at 700 degrees, this, the cationic and anionic part of this salt is you melt, they become free ions that in the through the two electrodes they can move and making the connection. But the most utilized, the one that will have much higher success, specifically for small scale, sometimes you are using this alkali fuel cell or the molten carbonate for big plants, for stationary plants, big power station. But we will never work on this. And here there are no membranes, not true at all, by the way. There are no membranes in principle. We don't need the membrane for the separation between anode and cathode. But here there are membranes for the reuse and the recycle of the carbonates and the product you are producing, etc. There are always a lot of membranes in this system, not just as in the core of the fuel cell, but still you have to use membrane also here. But we will not discuss at all. We will only discuss this one. This is a temperature from 50 to 120 related to the property of your membranes. This number tells you something. This 120 is the highest number in which an Nafion can work. If for any reason tomorrow you will have a better membrane that will have no problem in higher conductivity, etc., at a different temperature, this temperature will change. This temperature related only to the property of the membrane you are using. The fuel is hydrogen normally, or can be methanol. Today we have what we call a direct methanol fuel cell. So instead of injecting hydrogen that you have to produce continuously eventually, and hydrogen is not easy to storage. Hydrogen is dangerous. So you have to always try to, as much as possible, to produce continuously and to burn continuously. That's why people in the past, in the first experience, still today, when you go with this kind of system, you have a hydrogen tank on the back. But you must be very, 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 very careful, because if everybody is giving a crash on the back and you have hydrogen tank, that will be a big explosion. The benefit of using the direct methanol does not have this problem. So you can have your tank of methanol eventually on the back, and it's much more safe. And that's what we call direct methanol. But these are the two origins of hydrogen, basically. The electrolyte are sulfonated polymers, sulfonated because the sulfonic group is the one that can be ionized, and so the SO3H, H plus is the one that is going up and down. And the mobile ions is just H plus. Just to remember that H plus does not exist. Correctly, in this table is mentioned H plus for water, and at least 3 or 6 molecules of water are linked to H plus. If you want to identify H plus with any sophisticated system, does not exist. At least it's H3O plus. That means 1 molecule of water binded to the H plus, okay? But that's why it's written this way. When you are going to the alkali fuel cell, temperature is much higher, because that is a question also to have good mobility of the ions. The fuel is the same, and this will be basically the same in many of those. The electrolyte is just alkali, a solution of potassium, and the mobile ion is no more hydrogen, but is just OH minus. So you need also different kind of membranes, different kind of system. Here is the same H plus, the phosphoric acid, molten carbonate. This is just the molten carbon. The hydrocarbons can be the fuel or a CO, in this some case. The same here for this solid oxide fuel cell. And the solid oxide, remember we discussed already, mentioned also some perovskites, etc., can be utilized in this kind of system. You can see here, you have to activate at very high temperature, in the same when you want to melt this carbonate. But in this case, you can use hydrocarbons as also as fuel. What's interesting, and one of the reasons for working basically on this kind of fuel cell compared to all the other one is the power density. That means if you look to the ratio between the power, the watts that you can produce per weight, per kilo of your system, which is quite important on a car, means the cost of how much you are burning, you see that this number is 1 order of magnitude higher than all the other one. That's why in perspective, these kind of membranes are the one in which there is a lot of attention and trying to make progress. This core of the system is just related to this material for forming your ion exchange membrane, selective, able to transfer only this H plus that we were, H3O plus that we saw before, and you see there's a name, Nafion, because for today most part of the real system in real life is only one membrane all around the world, and that is a problem. If we don't have at least 3, 4, 5 different membranes produced in different countries, etc., there will never be a real utilization on large scale, because if there's no competition, these kind of things don't work. So today there is a lot of interest to try to produce a better membrane than this one, or alternative to Nafion, including here Danyang, including our place, etc. There are some other polymers similar to Nafion or totally different. Polymer with just, where you can induce some sulfonation eventually. Polyether, ether, sulfone is under investigation, but there is a lot of other alternatives and more, if some of you will have some good idea. The advantages of this kind of membrane that they operate relatively at lowest temperature than all the other one, which is something quite useful. They have the highest power density, and they are using a solid electrolyte, which is very easy to form in a very thin layer. All the membrane we have been studying until now, the highest thickness was 100 microns, but there can be 20, 10. That means a single cell with this power density for a single cell can be multiplied thousands of times and making a big package, big truck with 1,000 single cells. If you want to do the same with solid, with carbon, etc., forget. That you can have a totally different geometry, totally different footprint, etc. So a lot of interesting points. Where are the limitations? First of all, cost of these membranes and also durability. When everybody here is doing a test, remember that the first test you have to pass for your membrane to be utilized, to be accepted to the competition, is having 5,000 hours operation. That is the minimum. If you don't overcome the 5,000 hours, you can make publication, but it will never be of interest to anybody, because that means this system has to work, and the 5,000 is a number that's becoming famous and which is not easy to do better today. The other limitation is that for the kind of reaction we have today, we need a catalyst for the oxidation and reaction. This catalyst is palladium, which is expensive, but more than the problem of expensive is the fact it's limited, as we know already many times, from the tolerance to CO. And just because here we are sending hydrogen, and the hydrogen we are producing is always full of CO, all the problems that you have been learning and that now you understand. If you want to use this kind of system, if you want to use this kind of catalyst, and if you want to use this kind of membranes, you have to be able to overcome, to produce hydrogen clean enough and in system that the one we have been discussing. That's why the interest in trying to do this kind of things. And a lot of application that is that you can see here, and portable electronics, cars, both domestic and distributed power generation. So there is a lot of motivation. You can see, however, that the kind of fuel cell that we are discussing, this PMFC, are the ones that are just covering the widest spectrum of possible application. If you want to go to very large one, this for distributed power generation, the one that in this case, this solid or the molten carbonate, etc., have some role. But this one will never compete in this area here for a lot of different reasons. So that's why the interest is basically there. What we are talking about, We are talking about a system, as I was mentioning, which is nothing more than the Nernst equation that we have been assuming you have been studying in a fuel cell with the kind of electrical work that we are producing is related to the change of the free energy, the Gibbs free energy, which is nothing more the delta G that are given by the voltage for the Faraday for the number of the electron that you transfer per mole of reactant from the one cathode to the anode. F is the Faraday constant and has the voltage of the electromotive force of the cell reaction, which is the reaction we are considering. In most part of the cell we are considering, forget for the moment to make easier the story of the methanol, the reaction will be hydrogen that is arriving at the anode, and we oxidize with the hydrogen in H+, and doing this we just release the electrons that are starting to move in the external circuit, plus the oxygen, and we form water. So when we were discussing about the environmental problem, etc., that's ideal because we produce water in principle, and just we consume oxygen, which is already in the air. Unfortunately, hydrogen is not in the air, so we have to produce it, but for the rest, there is no significant problem compared to all the other way. When we are working the open circuit, the open circuit voltage is given by this voltage here from this equation is given by delta G molar, this is divided NF. And delta G is the molar Gibbs free energy for water formation. Keep in mind that this is important to remember because in terms of number at the end, you have to consider this kind of the value of this delta G, which means the final electrical work you are able to produce, is also related to the kind of to the state of the substance that you are utilizing. For example, the water can be in vapor phase, can be liquid phase, and the delta G is different. So when you make the calculation or when you read the numbers, be sure what you are reading to be consistent and to check and to make the right comparison. You have to know that delta G depends from the temperature and from the state, liquid or gas of the water. At 80 degrees, this delta G is minus 228 kilojoule per mole for liquid, and 226 kilojoule per mole for gas. So it's not a huge difference, but it's a difference, and if you want to make your calculation, you have to remember about this. That's why you can define this voltage for which is 118 for liquid water, 117 for gas water. The maximum energy efficiency is given by the ratio between electrical energy produced per mole of fuel and the variation of the enthalpy for full combustion. And that is basically the heat that you are producing in the system. And so it's given by the efficiency, just this ratio that is given by the maximum efficiency, delta G on the delta phi, the enthalpy that you are producing. And that is what we can have. This is theoretically. In real life, far away from the numbers that you can calculate from just this simple equation. And the difference is related, as you learned already very well, nothing to do, here in this case there is also something to do with the membranes, intrinsic property of your membranes. But in principle, most part of the phenomena that make a difference between the theoretical voltage and the real one that you are working on is nothing to do with the membrane itself, has to do with all the interfacial phenomena or the phenomena which take place in the system that we call concentration polarization, thermal polarization, over potentials of different kind. These are the ones that are changing don't give you the number that you can obtain just making a simple calculation in this with the delta G and delta H of the transformation that are taking place in the system, hydrogen plus oxygen, etc. And as you can see here, the difference is not small. The phenomena are exactly the same for all the membrane system, and we call activation losses. That means related to how the catalyst is working basically at the interface. The activation losses are related to the kinetics of the electrochemical redox. Catalysts are controlling the kinetics of your reaction, taking place at the electrode-electrolyte interface. So that is the called also activation over potential is the other term. The other one are the ohmic losses, are due to the resistance of the individual cell components, electrolytes, electrodes, current collector, etc., and to the resistance due to the contact problem. Ions has to migrate from one side to the other and to arrive to the interface, and any resistance to the transfer, etc., has to be as an effect on the overall voltage. And finally, the most important one in this case is the concentration losses. That's exactly what we call concentration polarization, basically, caused by the mass transport limitation of the active species during the cell operation. So we have all this kind of effect. Activation losses, just at the interface, related basically to kinetics phenomena, that is catalyst behavior, basically, that for different reasons, can be temperature, can be poisoning, can be kind of catalyst, don't operate as expected. This is the ohmic losses, all the resistance that you can just create in the system, and this is just concentration profile, which are not linear, but the ions has to migrate from one side to the other, and any resistance to the migration has an effect on the concentration, and that effect on the concentration is transformed in the effect of the overall voltage of your cell. So from this theoretical value that you calculate, as we saw before, from this definition of the voltage, you have this loss here, ohmic, activation, and concentration effect when you plot the typical voltage curve as a fuel cell. Can we anticipate and predict this kind of phenomena? Exactly in the same way, nothing different for what concerns the concentration polarization that you already have been discussing and studying in reverse osmosis, in gas separation, and similar. Basically, what you are doing here, you can arrive to calculate what is called the limiting current in this mentioned in fuel cell, here mentioned in electrodialysis, which is exactly the same story. Limiting current will be the current which there is no ions arriving to the interface where the phenomena take place. If there is no ions going through your membranes, because it's limited by the concept, if the transport across the membrane is faster than the transfer from the bulk of the solution to the interface, at one point there will be no ions to be transferred across the membranes. Your concentration profile is going down. We've been discussing this in reverse osmosis, we've been discussing this in gas separation, etc. Exactly the same story here. The only thing here, this is becoming a limited current. That means a lower value than this, there is no ion, no current that is formed because there is no ion able to go through. There is an infinite resistance, basically, if there is no ion that make the cross flow. And for doing this, we will use exactly the same kind of approach, the theory of this interfacial stagnation layer, to calculate just this kind of current. So the internal, the transmembrane flux of your ions in the membrane phase is given by the diffusion plus the migration, and this is diffusion and migration flux within the boundary layers, and the total flux can be also be defined in this way. There's one number here that I don't know if you are familiar with, that in this case you will utilize very often, which is called transport numbers. And in the specific case that we are discussing of the ion exchange membrane, this is the transport number of the counter ion in the membrane. And you remember what does it mean. Ion exchange membranes, I don't remember, we don't have here. Ion exchange membranes are systems in which you have a polyelectrolyte, which is characterized as a polymeric system, where along the chain of your polymer there are some negative group, for example, part of the chain, block, and some other one positive that will neutralize with the negative one. Now the system is such that if you want to have two ions mobile, you have to break the chain, because the negative one in a negative polyelectrolyte is fixed, is part of the structure. So we have one ion able to move and to counterbalance the fixed one. Another one, the fixed one, does not move. And you remember that we define it, I think you remember because I think we spoke sometime, or we spoke in spring, the Donnan exclusion phenomena. A Donnan exclusion phenomena is just telling you that the concentration of the co-ions we define it counter ions in the membranes are the ions having a charge different from the fixed one. And co-ions are the ions having the same charge of the fixed one. Now, the counter ion are the one that cannot penetrate. Sorry, the counter ion, you have avoid to violate electron neutrality. Now, if you have one ions with a positive charge, a negative charge, and the fixed one is negative, the negative charge cannot enter because there is not another negative that can go out without breaking the chain. If there is a positive one is entering, another one is moving out, and the electron neutrality is always respected. So when we call the co-ions are the ions having the same charge, and the counter ions are the ions having different charge. We define a transport number as the ratio between the amount of current transported by one ions respect to the total current that is transported across your membranes, which means that if you have membranes with no selectivity, positive ions and negative ions both will go across the membranes. So the transport number will be 0.5. If you want to have a fuel cell in which only proton H plus has to go through, that has to be 1, not 0.5. Otherwise, it means that some other ions are going through. And that is that this one has to be 1. All the current will be transported only by the H plus ions. For the other side, there will be no current transported by ions with a different sign. And that is creating interfacial phenomena at the limiting current, because at one point, the ions that can go, if these ions are moving very fast across the membranes, the protons, and you don't supply enough protons to the interface, the resistance is becoming very, very high, infinite, and nothing happens. And that is the highest current, limiting current you can realize. Okay? Anyway, we will continue and discuss this next time. How many of you are familiar with fuel cell? Making membranes, or making also studying the polarization phenomena? You do both? Polarization also, or only the membranes? Are you making also study of limiting current?
Just making a membrane and test some truth effects.
So you characterize for each kind of membranes you are producing. You have the impedance spectroscopy. Are you using impedance spectroscopy?
Yeah.
Okay. Anyway, we will discuss a bit of this. Impedance spectroscopy, this kind of problems years ago were very, very unknown, basically. If you go to famous book from Glaston about electrochemistry, there was no mention of this kind of phenomena, which take place not inside, not just at the electrodes, but just in the bulk. And that's why I was asking, with impedance spectroscopy, where you're working with alternate current, you can separate the effect, for example, of diffusion, migration, or formation of double layer with time, etc. That's why these are interesting for character and for understanding phenomena of this kind. Okay? See you next week.